All right, so our next speaker is Colin Johnson, who will be talking about symbolic regression and information measures. Yeah, thank you.
Yep. Okay, so what I wanted to talk about today is something I've been messing around with in a rather empirical way for a while, and I was hoping to talk about this, and perhaps the next stage of this is adding a more theoretical foundation to this. And this starts from this idea of symbolic regression problems. So, you know, we're trying to build expressions to model data. And the question I'm interested in is does a sub-expression provide relevant information towards solving the problem? And then can we add that sub-expression to a collection of useful components and gradually accumulate information that's relevant to the task? So there's this problem, the symbolic regression problem. So given a data set and a collection of operators and perhaps constants, find an expression from those that uses those operators and constants to fit the data set. So there's a long tradition of work in this area. So this starts from work in the 90s. Koser and colleagues introduced this idea of genetic programming as a way of automatically creating expressions. Yes? Sorry, I will stop moving around. I will stay here. I'll stop joking around. Okay, yeah, so there was a stream of work that was started by Koser and colleagues around this idea of genetic programming, using evolutionary algorithms to evolve program code to fit data sets. And this led particularly to this idea of symbolic regression, this idea of evolving or learning mathematical expressions to fit a data set, free-form mathematical expressions. And this has been taken up particularly in recent years by the physics community. There's a paper from about 10 years ago by Schmidt and Lipson that applied this to some physics problems, and then recently there's been a number of papers, Cranmer, Bartlett, Ferrer, and so on, who've been using this to do interpretable modeling of large-scale data sets from physics, from high-energy physics, from astrophysics, and so on. So there's been a renewed interest in this area in the last few years. So historically, the traditional approach to this has been, as I said, this genetic programming approach. So the idea here is we've got an evolutionary approach to finding some kind of expression that will match, that will fit a data set. So we start with a randomly generated population of candidate expressions. There's lots of different work in the literature about different ways to represent this, and quite a common one is through these tree-based representations, and then you're measuring some kind of loss, some kind of what's typically called fitness in this area of each population member, selecting the ones that fit the data the best, and then forming a new population by making changes to the code, so doing mutations and crossovers on the code and repeating that until error is below some threshold or until some kind of timeout. So we've got that approach to it, and then there's other approaches. There've been some alternative approaches in recent years. So there've been non-evolutionary approaches to this, searching a grammar of expressions using dynamic programming, doing a structured exhaustive search of a certain constrained expression space, using neural net type structures with the to evolve or learn symbolic networks of symbolic units, or using combinations of neural and symbolic learning, or using deep reinforcement learning to generate these kinds of tree expressions. So there's a lot of different approaches to this, but what unifies most of these is the focus on the whole expression. So we're trying to use some kind of candidate expression and modify or evolve that expression to fit the data. So there's a focus on sort of detailed fit to the data rather than, oh, that's weird. What's happening there? That's very bizarre. Make my thing appear like that. So there's a focus on sort of detailed fit to data rather than the overall shape of the solution. And in particular, one problem with a lot of these symbolic regression problems is the symbolic regression approaches is that an oversimple solution that doesn't have much room for development through mutation can dominate in that population. And there's been an approach called the wave approach. There's a couple of papers on this a few years ago, which found simple expressions and fixed them and then tried to evolve another expression to add on to that or to be combined with that in some way. But the resultant expressions can be very complex. There's a kind of cold start problem at the beginning of the run. All the expressions in that initial population can be very distant from the target. So that can prove very difficult to get things going. And there's some attempts at this, there's some work on this, including something that one of my PhD students did a while ago about diversity of in that population. And then there's standard issues around complexity of solutions versus accuracy of fit, overfitting and so on. And in particular, because these symbolic expressions give a lot of freedom for expressions to become very complex. So there's problems both at the oversimplicity and overcomplexity ends of the spectrum here. So I suppose the question I'm asking, the sort of big question I'm asking is can you decide what's relevant? Can you decide what sub-expressions are relevant? So not, how much, oh, thank you. Thank you. So not how much error is there between a whole candidate solution, so a whole mathematical expression of the data set, but a question like how relevant is a particular sub-expression to that data set? How much information about the problems gained if we add the results of a particular sub-expression into a feature set? I suppose this fits with the general idea that the evaluation of a good expression or a program is a kind of information accumulation engine. So if we think about a program, a working program, then after the first line of that program's been executed in some informal sense, the computer knows more about the problem than it did before. After another line, it knows more in some sense. There's more information in that execution that's relevant to solving the problem. There's no magic happens at the very last line of the program. It's when we get to the last step of a program or an expression, or the last operator in an expression, last step in an expression evaluation, we've almost all the information we need. We just need to do that last step. So I've been trying to do some empirical stuff to try and find a way of quantifying this. So what are we doing here? We're using some kind of measure based around the Gini coefficient to do this. So we've got a traditional setup for a symbolic regression problem. We've got a data set plus a list of operators. So these might be mathematical operators, constants, and so on. And then we've got a loop. We construct either all the combinations of features with operators, or if it's a larger feature space or operator space, a random sample of those. Then we calculate some kind of information gain metric that tries to measure the relevance of the expression to the problem. And I'll say that in the next couple of slides, how we do that. And we choose the expression with the strongest information gain, add that to that expression list, and then have some criterion for whether to remove the features that contribute to that combined feature until either the solution's found within a certain tolerance or we time out and fail. So I think the interesting step here is how we do this information gain, and that's what I'm keen to, I've got something that's quite simplistic and empirical at the moment. I'm keen to talk to people about how we could about alternatives to this. So at the moment, we've got what I've been calling clustering entropy. So we introduce some measure where we cluster within the feature space. We have a hyperparameter that's a number of clusters. We cluster within the feature space for the features that we have, and then we create a new candidate feature. So we're going to create a new feature. We're going to work through these, and for each one, we're going to create the existing set of features plus this new feature minus the things that contribute to that new feature. And then we're going to create a set of clusters of those, and then we're going to calculate this Gini coefficient of the values in that cluster and sum those to find a final value for the relevance of that sub-expression. So the intuition here is that if the new feature contributes a lot of information to the problem, then groups of similar instances will create less diverse groups within the target space. So the Gini coefficient will be small, so we can use that as a measure. So let me say a bit about this in detail. So we've got a typical sort of matrix of features and a target value, typical regression type problem. And then we say we're going to create a new expression. So we're going to create a candidate expression. So here we're summing together two of the original features. And then we say, well, okay, we'll put that feature in, this new feature in, and we'll remove the two, temporarily redact the two source features, the two features that are making that up. So this is now what we're using to predict that. So we do clustering on this thing without the target, on this side of it, on the feature space, and then we look at the target. So we say we've got the target, and now we look at the groupings of those target values according to that clustering on the feature side, and we see how diverse these are. So we use this Gini coefficient, this measure of diversity within that, to decide how diverse each of these is. So we've got a measure of diversity, and then we add those together to get a final thing, which is doing this strange thing on this side of the screen. So we get some kind of measure of that and this is what I'm using as the relevance measure for that new feature. We've grouped together on the feature space side. We've then looked at that on the target side, and we've said how diverse are those features on that side. So then we repeat that. So we need to then say, have we now eliminated those original features? Have we now extracted all the information, or as much of the information as we can, out of it? So we repeat that calculation with the original features and with the included as well, one by one and together. And if there's minimal change, again, there's a threshold hyperparameter here, then we eliminate the original features. So let's have a look at an example here. So I'm learning how to find these things that are going missing now. So let's generate an artificial data set of 500 values. Let's sample randomly 4 variables and calculate a function of them, and then we'll add some Gaussian noise to the target so that it's makes a slightly more challenging problem. So we've got this data set, and what happens? Well, we run this for the first time step, and we rank these candidate features by that sum of Gini coefficients there, so that relevance measure. And we find that, if we look at the expression, x0 times x1 over x2 plus x3, we find that both of those are then appearing within the top of that list. So what we're doing at the moment, we're in this version of the code that I've got at the moment, we just take the top one. I think we probably need some criterion for deciding how many to take. But for now, I'm taking them one at a time. So I take the first one. So it's discovered that x0 times x1 is what it thinks is the most relevant feature. That's the highest ranked in terms of this relevance metric. So we add that to our list of variables, and then we do that procedure for deciding whether we can eliminate it. So we repeat this with this included and the x0 included and x1 included and x0 and x1 included. There's a threshold for how much that's improved, and then we say, can we eliminate it? And in this case, it's the amount of additional information that's adding is sufficient to say that we eliminate that variable. So now we've gotten rid of x0 and x1 because that's sufficient to capture what was in those two variables, what was encoded by those two features. So we repeat that next time. The most relevantly ranked constructed feature is this one here, x2 plus x3. So you can see we're building up gradually this expression. So now again, the elimination test says that we can get rid of that. So we say true, we eliminate it. So now we've eliminated all of the original features, and the only remaining things are 4 and 5. Don't know what happened there. What's happened? Oh dear, there's been a problem apparently. Sorry. I think PowerPoint crashed for some reason. You want to?
Yeah.
Yeah. We can. So we need to, do we need to share that?
Yeah, we need to share.
I think we probably do. Going on the Zoom there. I think that's fine if I maximize that. If I maximize the window, I'll just do that. This is only 2 or 3 more slides to go. So can you see that on the share? Is that on the share yet? Yeah.
Yes.
Yeah, thank you. So we'd got to this stage, we'd eliminated all the original variables, and we constructed 2 new features, which are x0 times x1, x2 plus x3. So they're the ones that were in the original expression that was used to generate the data set. So we seem to be doing well here. And then the final step, the highest ranked constructed feature is now that division, and that's replicated the original source that was used to generate the data set. So that's now below a certain threshold. So the code stops at that point and says an approximate solution has been found. Well, actually, the exact source expression has been found, but it doesn't know that. It only knows the data set. So we have that. And I've done a few experiments with this, just on some simple expressions. So a lot of the time, perfect solutions found in in a small number of steps. When we get into slightly more complex expressions, we're not always finding it. And interestingly, there's different runs. So a different run will be different because the data set is generated randomly each time. So I thought it was interesting that sometimes a different approach is found. So here we discover x0 plus x1 plus 2 times x2 times x3. This time we discover it by discovering x2 plus x3 plus x0 plus x1, then adding on x2 plus x3. So the route it takes can sometimes be a bit different. So just a couple of slides to wrap up. So there's some issues with uneven cluster sizes. So for some kinds of expressions, you get very uneven cluster sizes. And I wonder if there's a way of using a clustering algorithm that generates even cluster sizes to do that. Finding a way to rationally choose the cluster size, that's a hyperparameter that we have to put in at the moment, or using some continuous alternative that doesn't use explicit clusters. Being more systematic about when to eliminate variables, again, that relies on another hyperparameter. Structuring the search more, perhaps searching first for coefficients, then operators. As I said at the beginning, having a stronger theoretical understanding to support the intuition and the empirical results we've got here. So I just wanted to finish with a couple of analogies. And I suppose there's an analogy here with decision tree induction. This is where, in a way, where the idea came from. Yeah, there's a long tradition of machine learning approaches going all the way back to ID3C 4.5 and more recent things like the various things like XGBoost and so on that choose features using information gain metrics. Yeah. And what I'm trying to do here in some ways is generalizing this. So we're saying, you know, decision tree induction is like this, is similar to what I'm doing, but if is the only thing in the operator set. And we're trying to use that same structure but to expand that operator set. And similarly in these boost type algorithms, we're determining that information gain of the various weak learners and we're combining them in a fixed way. And perhaps we can find a bespoke expression in this way. The second analogy is with feature construction. So in data mining, machine learning, there's ideas of feature construction, feature engineering. So we have a process where we're generating features, we're doing some kind of feature construction process, we've got some constructed features, and then at some point we hand that over to say a traditional regression algorithm or something like that. So we can see the approach here as being what we might call extreme feature construction. Rather than doing feature construction as a preliminary step and then passing the process over to a regression algorithm, we just keep on constructing features until we've constructed a whole solution. So that's basically what I wanted to say. I think the directions here, this is very preliminary work. I want to test this on a wide range of examples, including non-artificial examples. Examples I've shown you have all been taking very neat expressions and generating data sets from them, noisy data sets from them. I'm interested in alternative ideas for measuring that task relevant information of a sub-expression. Can we draw on ideas like information distances, compression distances, and so on? Approximations to complexity as a way of measuring that. We've calculated this. How much more computation do we still need to do to find a model that fits the data? And perhaps looking at some examples that use a wider range of program expressions that are not just mathematical expressions, but tackling a wider range of program synthesis problems, looking at this as a way of, I did some work a couple of years ago using similar ideas for fault finding and fixing, and I'd be keen to revisit that and have a think more about that. So that's everything I want to say. Thank you.